All right, and we are now recording. All right, well, good morning, good afternoon, and good evening, everyone. Um, for today, we have Maria Dostert from EPLF speaking about semi-definite programming bounds for the average kissing number.
Thank you very much, and thank you very much for the invitation and also organizing this nice webinar. I will talk here about the semi-definite programming bounds for the average kissing number, and this is a joint work with Alexander Kolpakov from Neuchâtel and Fernando Oliveira from Delft. So first of all, what is the average kissing number? Here, I start with some example before I give a proper definition. So here in dimension 2, if you consider the packing of unit disk by hexagonal lattice, so you see it here on the left-hand side, each of the disks has 6 neighbors. So when you take then the average of the kissing number of this hexagonal lattice, the number is 6. So I think here more famous is the kissing number, which asks for the maximal number of unit spheres which can simultaneously touch a central unit sphere without intersecting. As you can see here, 6 unit disks can touch a central unit disk without intersecting in the interior. So now we are interested in the average kissing number. So, and we don't care about the radius. So we have no restriction on that. Can we do better if we would allow also different radii? So here we allow radii, also small radii, which we fill in the gaps. By doing that, you see that the large disks have now no longer just 6 neighbors. They are touching in total 12 the other disks. But on the other side, the small ones just touch 3 other disks. Since we take the average over everything, we see that it doesn't really help. So at the end, we still end up with the average, it should be 6, which is 6. But okay, we also don't need that it comes from a lattice. So what if we put it in a different way, that we here have many small disks putting around the central one, then this one has a large number of contact points. Yeah, does it help? Can we do better than 6? That's the question. Or also for higher dimension, what is the average kissing number? So that is something we want to work today on, and how to use semi-definite optimization to compute upper bounds. Okay, on the slide before, I said we take a hexagonal packing. So that is basically an infinite packing where every disk has 6 contact points, but actually for the average kissing number, we consider just finite packings. So here, packing of balls in Rn is a finite set of interior disjoint closed balls. And then we consider the corresponding contact graph, which is a graph with vertex set P. So the vertices are, each vertex represents a ball of the packing, and 2 vertices are connected by an edge if the corresponding balls do intersect. They are not allowed to intersect in the interior, so it means they intersect on the boundaries, so they touch each other. So the contact graph is basically the graph where each vertex represents a ball in the packing, and 2 vertices are connected by an edge if and only if the corresponding balls are touching. So the average kissing number in Rn is then, we denote it by Kn, is the supremum over the average degree of the graph G, where G is the contact graph of a packing of balls in Rn. So here to get the average contact points, it is the same if you have a vertex and the number of contact points of this ball is the same as if you consider the vertex and ask for the degree of that vertex. And we want the average, so we take the average degree. And here it's important we take the supremum. So if you go back to the example from the previous slide, if you consider just a finite packing, so a finite subset of these balls in the packing of the hexagonal packing, at some point we are stopping to add balls. So there are some of them which don't have 6 neighbors. They have less neighbors. If all of them would have 6 neighbors, we would have the infinite packing. But we can take a very large amount of balls in our packing, just need to define it. So if we take the supremum over it, we will get 6. So the supremum of the average kissing number of the hexagonal packing is 6. But of course, it doesn't have to come from the hexagonal lattice. It doesn't have to come from any lattice, and also it doesn't have all the property to have that all radii are the same. So still the question, can we do better than 6 in dimension 2? The answer is no. Köbe, Andrew, and Torsten showed that the contour graphs for packing of disk on the plane are simple planar graphs. And for planar graphs, we know that the average degree is always strictly less than 6. So if we go back here and we take here the points in the center of the spheres, we connect them by an edge if they are touching. So these two are connected then we get a planar graph. We cannot not end up in a situation where we connect those two and these two so that they are crossing, because here you see, here these two spheres are not connected by an edge. They are not touching each other. So we get at the end a planar graph, and we know the average degree of the planar graph is less than 6. So we know the supremum here is 6 is really the maximum. So the average kissing number in dimension 2 is 6, but we can never reach it exactly with finite packing. But what is with higher dimensions? So usually dimension 2 is the easy case. So for dimension larger than 2, the problem is unsolved. And yeah, so the kissing number is also a difficult problem, but that's at least solved in dimension 3, 4, 8, and 24. Can we use somehow the information about the kissing number to get good bounds for the average kissing number? That's the question we're looking at next. So what bounds can we compute? What are lower bounds? What are upper bounds? So first of all, lower bounds. The kissing number of a lattice gives you always a lower bound. As we also saw with the hexagonal lattice, the average degree of the hexagonal lattice is 6. So 6 is always a lower bound dimension 2. And you can also do it in all other dimensions. If you have a lattice and you take the kissing number of that lattice, that always gives you a lower bound on the average kissing number. So in dimension 2, we saw that the average kissing number coincides with the kissing number. But this does not always have to be the case. Actually, in dimension 3, we know it is not the case. So in dimension 3, the kissing number is 12. We know if we have a unit ball, we can put 12 other unit balls around the central one without intersecting, but not more. But Epstein, Kupperberg, and Ziegler proved that the average kissing number in dimension 3 is at least 12.612. So it is larger than the kissing number. And here you also have to keep into mind, we take the average, right? For kissing number, we know it has to be an integer, but the average kissing number does not have to be an integer, of course. Okay, so now we know some lower bounds. What about upper bounds? So here we construct now an easy upper bound, I would say. We take a finite packing P, and we consider each ball in the packing can have different radii, right? So let X be a ball in the packing, then Rx give us the radius of the ball X. So for each ball in the packing, R of X gives us then the radius. So let's consider the graph GPE, where the vertex set is the set of balls in the packing, and the edges, like I explained before, two vertices are connected by an edge if and only if the corresponding balls are touching. And that is in the contact graph of that packing. And let tau n be the kissing number in dimension n. So then the number of neighbors of the ball X with radius at least Rx is less or equal to the kissing number. So if we have one ball of radius Rx, then the maximum number of balls which you can put around this ball so that all of them have radius Rx, is exactly the Kissing number. I said before, I defined it with the unit sphere, but if you can rescale. So here's the point that all have the same radius. If you allow some of the neighboring spheres to have larger radius, then it can just get worse. So it is less or equal the Kissing number. So now we consider all edges. If you have here the canality of the edges, that is less or equal the following sum. So we sum over all balls and the packing. And for each of the ball, we consider the cardinality of the set, which is the number of neighboring balls, such that touching neighboring balls with radius at least Rx. So it's exactly what I've written here in the line above. Here, what is written here. Okay, but here we have less or equal because if the ball X and the ball Y are connected by an edge, so they are touching and both balls have the same radius, then this appears twice in this set. So once this one edge appears when we sum over X and once when we sum over Y. So it's less or equal. So for each of the set, we know this cardinality has to be less or equal tau of n. So the less or equal the Kissing number, like it is written here. And here we sum over all balls in P. So this is times the number of balls in P. Okay, so we have that the number of edges is less or equal the Kissing number times the number of balls. If you consider a graph, then the average degree of a graph is twice the Kissing number divided by the number of vertices. Number of vertices is here exactly number of balls and the packing. And if we use this inequality, we see it is less or equal twice the Kissing number. So the average Kissing number is less or equal twice the Kissing number. This gives us a pretty easy upper bound already. So it's not necessarily good upper bound because dimension 2, we know the optimum is 6 and the upper bound would here be 12. On dimension 3, we would get an upper bound 24. So we don't know how good this is because we don't know how bad the lower bound is. But yeah, so this gives us an upper bound by using the Kissing number. So what do we know so far? So first non-trivial upper bound. So from the previous slide, I called it trivial upper bound. So the first non-trivial upper bound was given by Kupperberg and Schramm. And they stated that the average Kissing number in dimension 3 is less or equal a plus 4 times the square root of 3, which is 14.928, which is way better than twice the Kissing number, which is 24. So Glazerian refines this approach and gives an upper bound of 13.955. And he also extended this approach of Kupperberg and Schramm for higher dimension and could beat the twice Kissing number upper bound for dimension 4 and 5. So for the other dimension, he also computed it for 6, 7, 8, but there the twice the Kissing number was actually a better upper bound. So what our goal is, we want to refine this approach by using semi-definite optimization. Since we want to refine their approach, I would like to explain their approach before I explain what we changed to improve the upper bound. Okay, first just some notation that we are all on the same page. 2 vertices in Rn is here by this dot I give the Euclidean inner product. Here we have the n-1 dimensional unit sphere. The distance between 2 points on the sphere, we have here by r-cross of xy. And by omega rho, I denote the surface measure of the n-1 dimensional sphere of radius rho. And if I don't write the rho, then we consider rho equal to 1. And the spherical cap in Sn-1 of the center x and radius alpha is given in the following way. We have a set of points on the sphere with the inner product of x be at least cosine of alpha. So, and the normalized area of this spherical cap here is then omega of the n-2 dimensional sphere divided by omega of the n-1 dimensional sphere. And we take here the integral from cosine alpha to 1 of 1 minus u squared, then to n-3 over 2. So these are just some notations which I will use on the next page so that we are all on the same page here. Okay, so how does this upper bound work? We have here a unit ball in black. So here in black, we have a unit ball. In blue, we have a sphere of radius rho. And rho is strictly bigger than 1. So it has to be strictly bigger than 1. And we are considering the dimension at least 3. Furthermore, we consider a ball here of radius r, and which is tangent to B1. Okay. What we are interested in is in this red part. So the intersection of this ball with this sphere of radius rho. Here, if you choose rho in the way r in the way that you have rho minus 1 over 2, so this rho minus 1 is this distance, and if you take here as radius less than rho minus 1 over 2, then you would get a ball which is just in this area, and the intersection would be empty. If it is not empty, the intersection is a spherical cap. Okay, and the normalized area of the spherical cap is then omega of this intersection divided by omega of the sphere of radius rho. And if you could now imagine if we increase r, so if this ball would be a larger ball, then of course the red part here, the normalized area, would also increase. So this an rho of r, which gives us this area of the spherical cap, is a function which is in r monotonically increasing. So, but how does this help us to get an upper bound on the average kissing number? So first, I will give a lemma, which I will not prove here, but we will need it to continue our construction of the upper bound. So if the dimension is at least 3, rho is strictly bigger 1 and r is strictly bigger than 0. So we have the same assumptions than on the previous slide. Then a n rho of r plus a n rho of 1 over r is at least 2 times a n rho of 1. So if you have here, then the red area is a n rho of r. If you would have now also a smaller ball here of radius 1 over r, and you sum up these two areas here in red, then it says this is at least twice than if you consider a ball of radius 1. Okay, so now one further definition, and then I will explain that. Then we construct together the upper bound, which got used for Clausiren's approach. We fix rho to be strictly bigger than 1, and we consider a unit ball at the origin. So, and then any configuration of pairwise interior disjoint ball tangent to the central unit ball covers a fraction of the sphere of radius rho centered at the origin, and thence n gives the supremum of the covered fraction over all configurations. So if you look here, in dimension 2, it's maybe not such an interesting example, but yeah, you have a packing, so which means here you have further balls, which you all have here arranged here, which are non-intersecting. They might have different radii, and for each of them you have here the normalized area of the spherical cap, and then you want to know, then you sum up these normalized areas, and you want to know how much of the sphere of radius rho can you cover by this. In dimension 2, it's not so interesting, because if you would continue like this, you would get everything covered, but in higher dimension, it is not possible. So in dimension 3, the density will be less than 1. So here, dense n gives us the supremum over the covered fraction over all configurations. Okay, so now we will prove an upper bound. So we have the graph G with vertex at P, where P is a packing in Rn, and edges E. And for each ball in the packing, Rx gives us the radius of that ball. So here we consider the following sum. So we sum over all edges xy in E and take a and rho of Rx divided by Ry plus a and rho of Ry divided by Rx. Okay, so if we consider the lemma of in the previous line and we just consider the sum of these two terms, here you see that this has always to be at least twice a and rho of 1. We sum over all elements in E, so we have times the cardinality of E. So here we just applying the lemma, okay? So then we consider with Nx the set of neighbors of the ball X in the packing. Now we consider here again, it's exactly the same sum as in the previous line, but we split it in a different way. We say we take here, we sum over all packings in the ball, all balls in the packings, then we sum over all neighboring balls of this packing and sum over a and rho Ry Rx. This is exactly the same as here. Before, if you have an xi, then you have also at some point sum here over y, and then you have x here, and then you have here the other way around. So this is just written in a different form, but it is exactly the same. Okay, so before we said if we have a unit ball in the center, and then we sum over the, we consider all its neighbors, and we sum over the area which of the corresponding spherical cap, then we get the fraction which can get covered by this. So here we divide by Rx, the radius of X, so that really the sphere in the center is the unit sphere. So, and this sum here is by definition then the density of n rho. So we know that this is less or equal the number of balls in the packing times density of n rho, because the density gives up the maximum which you can cover here. And here's one example, so it cannot get larger than this density. Okay, so now we put all this together. So these two bounds we computed here. So if rho is strictly less than 3, then a and rho of 1 is strictly bigger than 0. So you can imagine if rho is too large, then a and rho of 1 is 0. So there is no intersection. So therefore we have this assumption. So the average kissing number of or the average degree of a packing graph is equal to twice the edges divided by the vertices, which are here the number of balls in the packing. That's less or equal the density divided by a and rho of 1, because we just put these two sides here together, and then we get that twice the edges divided by p is less or equal the density divided by a and rho of 1. So here we get that the average kissing number in dimension n is less or equal this density divided by a and rho of 1. So here we have one construction how we can compute an upper bound based on this density. Okay, here in the theorem, I just restated again what I explained on the previous slide, so that for dimension at least n and rho between 1 and 3, we have this upper bound of the average kissing number. So a and rho of 1, we don't have to worry about that we can just compute is the normalized area of a spherical cap of radius alpha, such that cosine of alpha is rho squared plus 3 over 4 rho, and we can then just compute this explicitly for the dimension we are considering, so for n at least 3. But what about this density here? So the density can never be larger than 1. So what you can do is you can say, we make an estimate of the upper bound by saying the density is less or equal 1. And then you see, you get here the best bound if you consider rho to be equal square root of 3. And then Kupperberg and Schramm got this upper bound here of 14.928. And Glaserin got this upper bound dimension for 34.68, which is of course also here way better than twice the kissing number, which would be 48. sorry. And here also in dimension 5, it's 77.756. So if you consider now this approach and you would like to improve this upper bound, and one option is here, of course, to work on this estimate. I mean, of course, the density is always less or equal 1, but maybe you can also get a better upper bound than 1 for the density. And that is also what Glazerian did. He improved the upper bound in dimension 3. He also still considered rho equals square root of 3 and got an upper bound of 13.955. So you see, it is he could improve quite a lot the Cooper-Bertram upper bound by getting a better upper bound for this density. So before we saw that the lower bound is, I think, was 12.6. So it's still quite far from the lower bound, but yeah, he could improve the upper bound by improving this density. Okay, so our goal is now using semi-definite optimization to improve the value for the upper bound for this density. And yeah, so first I will give some observations before I will give the semi-definite program. So first, here AN rho is increasing in R, as I said, and has a limit because if you consider here unit ball, here the sphere of radius rho, and here ball of radius R, if R increases, of course, this red part increases. It can get larger and larger, but it can never exceed, it can never be larger than the case when it looks like this. So this value for AN, that you consider for AN rho of infinity. Furthermore, if you have 2 points on the sphere to check whether they are, they are contact points, and X belongs to a ball of radius R and Y belongs to a ball of radius S, then you can check that X, if the inner product of X and Y is less or equal 1 plus R plus S minus RS divided by 1 plus R plus S plus RS, then you know that the corresponding sphere do not intersect in the interior. So we want to find the maximal number of points on the sphere so that the corresponding spheres do not intersect in the interior. And for this, we need to have this estimate based on the radius of the corresponding spheres. We need to have here some bound saying when are they too close. So, and this fraction here, we denote by I pi RS, so I pi for inner product. Okay, and we are almost done. I will just give a few definitions, which we need also in the semi-definite program, and then I will show you the semi-definite program. So basically, David Delade and Fernando Oliveira and Frank Valentin published, they gave a semi-definite program which gives you an upper bound on the maximal density of the packing of spherical caps on the sphere with different radii. So basically this sounds like exactly what we need here. There's just one difference. In their approach, you have as one parameter a finite set of radii, and you say, for example, you consider radii 0.4, 0.5, and 0.6, and you want for this radii, if the spherical caps have those radii, what is the maximal density? But here, we don't want to have a finite set. We want to have an infinite set. We want to have, say, okay, in this whole range between rho minus 1 over 2 and an upper bound, the spherical caps can have all radii. So which makes the program a bit larger. Okay, so before I show the program, just a few notations. The first 2 lines in black is exactly what I wrote on the previous slide. Here, as usually, we are working, optimizing, we are using kernels, so real valued squared integral function on v times v, where in our case here, v is the interval between 0 and 1. And here in the program, you will see this notation here in this map. This means exactly the map from xy to fx times fy. Then we are interested in the principal submatrix of a kernel F. Here that is a subset, a finite subset between 0 and 1. And then the principal submatrix is when you evaluate FUV on those points on this finite set. And here we consider Jacobi polynomials of degree k, and alpha equal beta has to be n minus 3 over 2. So we are optimizing on the kernels on the sphere, and they are highly symmetric. And here we use we express these functions by using Jacobi polynomials, and we normalize them in such a way that at 1 it is 1. The program is quite large, therefore I will give you the program step by step. So we start here in the following way. So we are considering dimension at least 3. We are considering rho between 1 and 3, like before. Rho was the radius of the sphere we are considering. Then, if you remember the previous picture, if the large sphere has radius rho, and if the ball of radius small r, when this radius is less than rho minus 1 over 2, there's no intersection with the sphere of radius rho. So here, therefore, we say we consider radii which are bigger than rho minus 1 over 2, or at least rho minus 1 over 2. And then we say we make we define a maximum, which is capital R. Let's say, for example, if the radius is bigger than 30 or 40 or 50, then we say it is infinity. Then we consider the case like I made before in the picture. You see what is the limit value of A and rho. Okay, so we have radii between in this interval. It can contain each of this, attend each value here in this interval. So we have here not a finite set. It has to be between rho minus 1 over 2 and r. And here it maps from 0, 1 to this set. And this is an increasing bijection. Okay, then we have the following. We also need the surface area, so the normalized area of this intersection of the sphere with the ball, so which I draw in red before, and that we need in our program. But in a semi-definite program, we cannot, to put it in a semi-definite program, we have to express it somehow as, for example, a polynomial. So here we have also a polynomial from 0, 1 to r, which approximates this, the normalized area of the spherical cap where the radius is r of u, and we take here the square root of it. It can be larger than just the result get worse, but it cannot be smaller, so it is an upper bound. When we consider u equal 1, we consider for the infinity case. Okay, and then we have here, we fix d to make it finite dimensional, and we consider from 0 to d, so d plus 1, many kernels, fk from 0, 1 squared to r, and we have ftuv, and here is sum from k equals 0 to d of fkuv times the Jacobi polynomial p and kt. So t is between minus 1 and 1, so basically, if you remember the picture before, you'd have 2 points on the sphere. We call them x and y, so contact points, and t represents the inner product between those points. And since that 2 points on the sphere, the value can be between minus 1 and 1. Okay, and then we have also u and v between 0 and 1, and that comes just from here because r of u gives us, or r of v gives us the radius. So uv is between 0 and 1. So here difference is to the program. So I said this approach is based on the program from Delade, Valentin, and Oliveira. But here it becomes larger because of this infinitely many radii. And before in their program, f was basically a kernel valued function and matrix valued function. And in our case, it is a kernel valued function. So we say for each t, we have a kernel from 0, 1 here. So we have many kernels here. Okay, so for a semi-definite program, you also, of course, need some constraints. So here's first we defined all the variables we are dealing with. We have some positive semi-definite constraints. So every principal submatrix of F0 minus this product, which I defined before, which maps xy to A of x times A of y, has to be positive semi-definite. You will see on the next slide, I will prove the theorem in which step we need that. And so here for 0, we have here 0, and then we have just here by polynomial here 0, then this is 1. The second condition is every principal submatrix of Fk is positive semi-definite from k to 0 to d. So actually you just need k from 1 to d, because if this holds for F0, then F0 has to satisfy this. So this follows from the first one. And I defined before what means every principal submatrix, where we say take the finite set U in 0, 1 and evaluate then the matrix on all those points. And then we have one condition which says the function f at TUV has to be less or equal 0 whenever t is between -1 and this inner product RU/RV. And IP is what I explained before when we have 2 points to know whether they are too close to each other. We said it has to be less or equal 1 plus R plus S minus RS divided by 1 plus R plus S plus RS. And here R and S, the radii are here represented by R of U and R of V. Then the density is upper bounded by the maximum of F1 UU. So 1 you always get if the two points you chose coincide, because then the inner product of 2 points on the sphere is 1. Okay, so I will not give this proof in detail, also sheet at some points where I make it a bit faster, but just that you have an idea how's the relation here between it. So that delta be the normalized area of the sphere of radius rho covered by a configuration coming from a packing P, and assume that this delta is bigger than 0, and we adjust and assume that each ball has radius at least rho minus 1 over 2, because the balls in the packing with less radius don't intersect with the sphere, so it doesn't help us for getting this upper bound. So we just consider the ones which have radius at least rho minus 1 over 2. Let B be a packing ball in the packing. If its radius is in this range, so between rho minus 1 over 2 and R, then let U between 0 and 1 such that R of U is equal to the radius. So for each, I said before, this R is a bijection. So for each radius, we have a U so that R of U gives the radius. If the radius is not in this range, we said before it's not allowed to be less, so it means it is strictly larger. Then we deal with it like this. We are at infinity and we consider U equal 1. So now we can re-represent that each ball can be represented by X and U, where X is the contact point on the sphere, and U is such that R of U gives the radius of the corresponding ball. And then we can define the whole packing P we define with such an interval where we say, so such I, where we represent each ball with X and U. Okay, then, so why do we get this upper bound for the density? So first we sum over each 2 elements in this packing, where X and Y are the contact points and U and V are such that R of U, R of V gives the radius. Then we consider here f of x times y, the inner product, and uv, a of u times a of v minus au squared minus av squared. Since f, the way we build f is the Jacobi polynomials, and we have here as elements are points on the sphere, we can show that this is indeed non-negative. And in this part here, that's where I said I cheated a bit, because it's not hard, but we need several steps to get this inequality. But just to let you know where we need this constraint 1 and 2. So now we can split it in the following way, that we say, let's consider the case where xu coincide with yv and where they does not coincide. If they coincide, then the inner product of x and y is 1. and u is equal to v, and we have a of u squared. And if they don't coincide, they have to satisfy the last constraint in the program, then we know it is less or equal 0. Since it is a feasible packing, we know that t is in the allowed range. So we can skip that part. And then we have just minus sum of a of u squared over each of these tuple in the packing, and that's squared. If you put this on the other side, one can see that the sum of a of u squared xu in I is less or equal the maximum of f1 uu for u between 0 and 1. So this program on the previous slide gives us indeed an upper bound on the density for the maximal density, so that we have which gives the maximum, so the supremum over the fraction we can cover from the sphere of radius rho by packings. Okay, so the problem is we have here now, so nice thing is we have a semi-definite program, which gives us an upper bound. The bad thing is it is a very large semi-definite program. We have here these functions, we have here the polynomials we approximated, we need here these kernels, so it's a very huge program. So how can we make this solvable? So that's the next step. How can we compute this? So let's start with the kernels fk. How can we specify those? So we fix capital N strictly bigger than 0, and we have functions p0 to bn from 0, 1 to r. And then if we have a matrix A, r to the power of n plus 1 times n plus 1, then if we set f uv equal to this sum of this matrix times piu times pjv, we have the following property. If A is positive semi-definite, then every principal submatrix of F has to be positive semi-definite. So the second constraint in our program says that for F1 to Fd, every principal submatrix of F has to be positive semi-definite. That we can realize if we write F in such a form and ask the program to find a positive semi-definite matrix A, and then we write it in this form. But here we have, yeah, of course, we need also these polynomials, which we need to get somewhere. Furthermore, if we take also these polynomials and write A in the following way, that we have A is equal to alpha 0 p0 plus until alpha n pn, and we have this matrix aij minus alpha I alpha j greater or equal than 0 positive semi-definite, then every principal submatrix of F minus A times A star is greater or equal 0. That is exactly the constraint we have for F0. Right? And this we can realize if we use these polynomials and write, then we ask for a positive semi-definite matrix of that form. So we can rephrase our semi-definite program from a previous slide, and for different P0 to Pn we get different semi-definite programs. And here we need an interplay between the Pi and the quality of the approximation, because yeah, so A approximates this area, surface area, and yeah, we need to find Pi so that this approximation is also good. Okay, so we can everything express as a semi-definite program, but it really becomes huge. So here, therefore, we use two different approaches. So one approach is that we say, let's consider the Pi's as step functions. The other approach is we say, let's consider all the Pi's as polynomials. So we are first write a linear program. We look for polynomials, which approximates pretty good this map here, and use this polynomial in the semi-definite program. There we have a bit more freedom. We get better results, but the program becomes very large. We can also use step functions. With step functions, the results are not so good, but at least the program does not become too large. So here it depends on the dimension when can we use which approach. So how does this approximation look like? So we have one approximation. We solve a linear program to get a polynomial which approximates this pretty well. So here we have a polynomial of degree 6 in black that approximates here exactly this map where we consider dimension 3 row, and then for row we consider square root of 3, and we evaluate at r of u to the power of 1/2, so the square root of it, and that is the line in gray. And here we consider r strict it is to be 30. I said if r is small r is the radius is larger than capital R, we are considering the infinity case. So here we went until 30. And in the black thin line, you see our approximation by the polynomial. It is never allowed to be less than the gray line, which also never happens. Sometimes it's a bit above the gray line, there the approximation is not so good, but I think in general it is quite good, the approximation. And at the end here you see the small jump, because we have to make sure that for the infinity case a of 1, we have at least a in row square root of 3 infinity. Okay, so now we have these two different approaches. We computed these bounds. So in from dimension 3 to 9. In dimension 3, we have the lower bound, which was given by, which I have shown you at the beginning from Ziegler and his co-authors. And then we have here other lower bounds, which come from the kissing number of a lattice. What are the upper bounds, which was known before? These are the ones from Clausieren, which I have shown before. With this approach, the upper bounds in the higher dimension became larger. So I think in dimension 6, it was 170 and so on. So from 6 on, the 2 times kissing number was the best upper bound, which was known so far. So here we use the semi-definite program, use this approach with the polynomials. We consider d equal 10 and capital N, in the one case 6 and the other case 8, you know, where set the polynomials P0 to P capital N we use as an input to construct the kernels, and R equal to 30. From 30 on, we say we just take the case where we have the limit. And here we could improve the upper bound from 13.955 to 13.606. Now in dimension 4, here's quite a big improvement. So from 34 dot something to 27 dot something. Unfortunately, from dimension 5 on, this program was too big to be solvable. So here we run pretty quickly in numerical issues. So here we write everything with polynomials. We give them as an input. And then we have these non-negativity conditions, where we also say the function has to be less or equal 0 in a certain domain. This we also wrote with sum of squares conditions. So we have the end a very big semi-definite program, which gives us then the upper bound. We get it then as floating point from the solver. And in the paper about the exact semi-definite programming bounds for packing problems, that I wrote together with David Delat and Philippe Moustrou, we developed a library to convert to get from the floating point result to the exact rational solution. We just applied it here, and we had immediately the verification, which so these are rigorous upper bounds. Here we had we used the step function approach because it became way too large. Here we considered rho equal 2. N equals 30, so polynomial, the function P0 to P30. And here capital R is 184.25. And then after this value, we just say, okay, now we can take the infinity. But to keep everything small, we also have for the non-negativity condition, we just use sampling, where we had later then a bit more work to write the verification to have also rigorous upper bounds. However, so with the step function approach, you also see we could improve those upper bounds. Then we also computed the upper bounds with a step function approach for dimension 3 and 4. There they were worse. So I would assume if we would be able to solve this large semi-definite program with a polynomial approach, also in larger dimensions, we could even get better upper bounds. But unfortunately, that is not possible. So we had to use 2 different approaches. Yeah, so these are the new upper bounds we obtained for the average kissing number. Thank you very much for your attention. Do you have any questions? Okay.
Yeah, any questions for our speaker?
I have a couple of questions. Hi, Maria. So one question, I'm wondering whether the semi-definite bounds you got for average numbers, how they are comparable to the semi-definite bound for kissing numbers. So how, just curious how far these are.
You mean when you compare it here with the kissing number upper
Yeah,
bounds?
like Bashok-Valentin bounds, how far the results you get via the semi-definite programming would be from your result. Like how much you lose by adding more radii.
Yeah, I mean here it would have been the kissing number with the semi-definite program would be 24 dot something.
Yeah, but for say for dimension 3, just surely you can get you can solve the problem, but how much? Maybe 3 and 4 is not that interesting, but higher dimensions.
Higher dimensions. Okay, it depends on dimension. I mean, dimension 8 is also, I think, not so interesting, but
yeah, sure.
So I actually don't remember the upper bounds for the other dimensions. But what we could do here, we could also combine this with the kissing number, the 3-point bound for the kissing number to improve this. That would be a way to improve this. But yeah, I don't remember actually what are the upper bounds for the kissing number from Bashak and Valentin in this dimensions.
Because this is also effectively a bound on the kissing number as well. It's not some.
Yes, right. Yeah.
And the second question, why do you take rho equal to 2 here?
There we played around. So we tried rho equal to square root of 3 like before in the cases, but there we got worse bounds, and then we tried it with 2 and.
So 2 was the optimal? That is hard to believe.
Yes, so at least from the numerical experience. So I would not say 2 has to be the optimum.
Yeah. You by the way, you had a slightly incorrect note that I used rho equal to square root of 3. I actually tried to optimize for rho, and it was slightly different than square root of 3.
Oh, okay. Sorry. Yeah, that's good to know. Yeah.
But definitely not 2. Not even close. So I'm just
okay. Yeah. 2 would also not be good for dimensions 3 and 4. It was just for the higher dimension we saw. We get something better if we take 2 instead of square root of 3.
Okay, that is weird. Okay.
Yeah.
Well, thank you.
So I'm curious. So you mentioned this paper by Dostert, Valentin, and Oliveira, and they have covering of sphere with spherical caps with fixed radii, and you allow some freedom in the choice of spherical radii. So does it mean that as a byproduct you get that okay, these sets of spherical radii are better to cover with than these others? So can you make a statement like that as a result of this? So I mean, if you have an estimate.
If I would just say we consider a finite set, then we would make some restrictions, too many restrictions, right? That's not what, if you want to have an upper bound for the average and you would kissing number and you take a finite set of radii, then it would not give you an upper bound because you would miss something.
So I guess what I'm asking is, does it mean that you can say, okay, when you cover a sphere with caps from this set of radii, you get strictly better density than for this other set of radii?
I would
get this as a byproduct.
I would assume, I didn't test, but when you have the sphere and you want to know what's the maximal density that you can pack the sphere with spherical caps and you restrict the radii, so which radii you can use, then I would assume if you give more freedom that you say, you can have an infinitely many different radii, that you get something better. But it could, on the other hand, also be our program is way larger. It's the one from David, Frank, and Fernando. So I don't remember which degree they use. Maybe you could, in theory, get better with this, but not in practice, because our program is so large that we cannot go as high with the degree as they did. So yeah.
Thanks. So you only try these two values, sorry, you'd only try square root of 3. So I'm curious, so you do not, how difficult would it be to optimize over rho? So I understand it's already
Wow.
unpleasant.
Yeah. Okay, but you have it also as input, right? And you would have this as a variable and also in the range of the radii. So I would think that then it would become very large. So I think, yeah. I don't think that you can also optimize here also over rho.
Okay, how about PIs? So you tried these two classes. PIs are the coefficients in the kernels in FK, right? So you tried to choose PIs from two classes.
Here, yeah.
Yeah. So, okay, so polynomials I understand, but why step functions? Is there?
Yeah, we just used, maybe I can show it also here. We use a step function where we assign it then for each range, so the value, so we have an upper bound, because then you have just the value, right? It's not like, I mean, with the other one, we have polynomials of degree, I don't know, 16 or something, which makes everything larger and bigger. And it was, we used step function because we saw if we work with polynomials, it's not solvable in practice. And what can we do to make it, the program not so large?
So maybe would it make sense to try other functional classes, like, I don't know, piecewise linear functions or something, or is it just naive? I mean, it obviously is naive, but I'm curious.
Yeah, so these are the two kinds we tried. So, and I don't know, maybe there's also a different way to deal with the situation where you cannot use the polynomials. Yeah.
Thank you.
Were there any other questions for the speaker?
Hey, Maria? Hey, so I had a question. As somebody who's not familiar with these lower bounds, I wondered if you could just say a little bit about whether people just sort of expect whether those lower bounds are sharp or whether these upper bounds are maybe more reasonable. And then also, I wondered if people have kind of played numerically with the lower bounds and tried to find, like, say, in dimension 4, you had that lower bound of 24. I'm wondering if that's just, it seems like it's just from the kissing number, the regular kissing number, that lower bound, but would you expect something maybe larger if you played with it numerically?
Yeah, so here we use the kissing number of the lattice. We didn't find anything better, or we also didn't find when it works in this direction. We thought, okay, kissing number of the lattice is probably not a good lower bound, so there should be something better. And we put also quite some time and effort in it to try to get something geometrically, but we couldn't get a better lower bound. For dimension 3, the one which I showed at the beginning, there was copies of the 600 cell to get this upper bound here. We also looked at their approach and tried to generalize something, but we couldn't. But my feeling is that the lower bounds are not so good. I would assume that. So, I mean, I don't say that it is large, far away from the lower bounds, but I think dimension 2 is probably a special case where this is the same. So for my intuition, I would say if you allow different radii and you want to take the average, there should be larger than the usual kissing number.
All right, well, unless there are any other questions, let's thank the speaker again. All right, I'm gonna stop recording now.